Okay, so here we have our graph, and it depicts how the output signal slowly approaches that target or that input signal that it wants to acquire, so to speak. So what we have done here, we have hard-coded these 5% into the formula. So instead of having it this way, let's just create that as a variable and call it adoption rate and set it to 5%. Now that is an input field, that's what it looks like. And now this field, instead of calling it C5, we might as well call it alpha. So now in this formula, we can replace this 5% that we wrote in there with alpha. And down here where we wrote 95%, well, that's not 95, that's 1 minus alpha. And then we can take that formula and copy it all the way down. You see the numbers didn't change, just the formula changed. And from now on, that formula calculates alpha. So it's the new value times alpha plus the old value times 1 minus alpha. And not much changed here in this in the graph. Just to be sure that we see the first 6 seconds of this of time, let's right-click down here on the axis and then go to, just right-click on Format Axis. And then you can give it a maximum value of 6. And that means it takes, as soon as it redraws, you can see it here. There's the 6 seconds, so we see the first 6 seconds. So we can start playing around with it. If we increase, for example, the adoption rate from 5 to 10%, guess what happens? The graph will adopt that new value quicker because it approaches that new value by 10% every frame. So for every frame, the output signal approaches that new value. It responds quicker. Similarly, if we go from 10 down to, let's say, 3%, then you see the filter is a lot slower to react. It takes 6, 8, 9, 10 seconds before the filter will even reach somewhere close to the input signal. Okay, so change that back to 5%. It's somewhat of a nice value. And now there's something else that we could change. Here we could, for example, use the time increment and just giving it a value 0.1. This is an input field, and instead of just writing down the number in here, we could just add a formula equals this cell plus the increment. And because we want this to be an absolute, not a relative coordinate, we have to add these little dollar signs. So from now on, this will be always taken as that cell. We copy it all the way down. Again, you can see no changes, but in the formula we now have a reference to that time increment. That means if we change that time increment to example 0.2, it will change the increment at which this time is being triggered, so to speak. So just out of curiosity, put it back into 0.1. Okay, there's one more thing that we need to change. We have hard-coded this 0 and this 1 into the input signal. So again, what we want to do is replace that with a formula. So we could write equals if, now there's a condition, and the condition is this cell is less than 1, semicolon. Then I want you to put in a 0, else I want you to put in a 1. Close the bracket, and that's it. Now if we take that formula and we copy it all the way down, you will see it will automatically create all zeros appear, and as soon as the input value is 1, it'll create a 1 for me. So there's one little error in that formula. If A9 less than or equals 1, then it's a 0, and if it's not, then it's a 1. Take that, copy it all the way down. Okay, so now it's a correct behavior. It's all the way 0 until the time 1, and then as soon as it's more than 1, the input signal, boom, jumps up to 1. What you can see here, that's an artifact. So as soon as you scroll away, come back down, and the graph is redrawn, and you will see it. So we now have the time, the input, and the output are all dynamically generated, so to speak. And if we play around with the increment, for example, if we set the increment to 0.2 2 seconds, then you see this whole thing spaces out a little more, so there's just less frames a second. And that's the next thing that you should learn about low-pass filters. If you change the adoption rate to, let's say, 10%, this thing reacts quicker. If you increase the adoption rate, it'll adopt the new value quicker. But at the same time, if you increase the time increment between the frames, then this whole thing will react slower. I mean, it doesn't surprise because it's an adoption rate per frame, and if there's less frames in a certain time, the whole filter thing will react a lot slower. So let's just put this back to 0.1, or probably better to 0.05. So we get an update every 20th of a second. Again, as you can see here, it's all zeros, and then as soon as it's more than 1, it jumps up to 1. Now you see that the values are ending at the 3-second mark. That's because we just didn't calculate any of them. So just take these and then extend them all the way down. You can actually extend them long way down. Yeah, that's just fine. And you see they're still not there, so what we have to do is mark one of these graphs, and you see the scope of that graph. So we have to take these boxes and drag them all the way down to where we want it. So until 6 seconds, that's probably just fine. And this one as well. So we see the graph extends. We do the same for the input signal. Here we have it. And the X values, damn it. There we have them. So now we can take a closer look at it. We see the first 6 seconds. And so what you can see, if I increase the time increment or the frame rate at which it is being processed, then this thing will react quicker. It will behave as if it was a quicker filter. So be aware that the adoption rate as well as the time increment, or the processing frequency, so to speak, influences the behavior of the filter. So you can play around with it any way you like, have that Excel file, play around with the adoption rate, with the time increment, and you can see how this filter system changes, how it reacts quicker or faster. An increased adoption rate will make it react faster. An increased time increment will make it react slower. Yeah, play around with it, keep enjoying, and the next thing that we're going to do is build a higher order low-pass filter, and then you can see how things change with higher orders, because more smoothing, as some people call it, isn't necessarily achieved by using a lower adoption rate. Sometimes it's better to leave a higher adoption rate, but use a higher order filter, and we're going to talk about that in the next video.